Hey everyone, welcome back to The Explainer. I'm really thrilled you're joining us today because we've got a fascinating piece of AI news to unpack. If you follow this industry, you've heard all the hype about computer vision models and their pinpoint precision, right? But let's be totally honest here. We've all been there. You're standing in front of some smart kiosk at a museum or maybe a mall, waving your hands around like a total weirdo, and the machine is just stubbornly ignoring you. It's frustrating. You know firsthand there is this massive disconnect. Well, today, we're actually breaking down a brilliant piece of engineering analysis to figure out exactly why real-world, public space AI gesture systems completely break down, and, way more importantly, how we can actually go about fixing them. Okay, so let's dive right into this. There's this huge myth floating around the developer community that high frame-level accuracy automatically equals usable interaction system. Like, it's just a given. But you can have a totally state-of-the-art model that identifies a hand landmark with, say, 99% precision, but the absolute second you put that system in a busy public plaza, it completely falls apart. You see, academic pipelines, they usually benchmark per frame accuracy, but hitting a super high score on a static dataset, that is an entirely different beast from actually confirming a fluid, unpredictable human gesture in real time. So here's our roadmap for today's explainer. First, we'll look at the recognition to interaction gap. Then, we'll go inside the kiosk repair logs. Third, we'll cover the 6 ways gestures actually fail. After that, we're moving from frames to events. And finally, building better public AI. All right, jumping right into section 1, the recognition to interaction gap. Now, this gap is really all about the stark contrast between a totally pristine development environment and the beautiful chaos of a real-world deployment. Think about how these AI models are trained and tested in the lab. The conditions are literally perfect. You've got fixed frames, controlled lighting, predictable distances. And usually the users testing it know exactly how to behave for the camera, right? But out in the wild? Completely different story. Public spaces have harsh backlights, crazy screen glare. Users are standing at wildly shifting scales. Some might be 2 meters away, others are right up, practically pressing against the screen. And unpredictable humans, they definitely don't follow an experimental script. We're talking overlapping hands, super rapid movements, and just completely shifting poses. So the crucial point we really need to anchor on is this definition right here, the recognition to interaction gap. Basically, this captures the exact situation where your low-level vision model is producing accurate frame-level hand landmarks, but those outputs just completely fail to become interaction events that the user can actually perceive. Because remember, users out there do not care or even perceive whether the mathematical coordinates of their pinky finger in a single isolated frame are correct. They only care if their physical action actually triggered the intended event on the screen. That's the whole shebang for them. Moving on to section 2, inside the kiosk repair logs. All right, it is time to put on our investigative hats. We're going to do a bit of an autopsy on some real-world data from a scenic aerial public kiosk. The source material we're digging into today is incredibly unique. These researchers didn't just run some sterile, isolated lab study. No, they analyzed exactly 8 engineering experiment and repair records from a live deployed kiosk project. So this right here, this is our forensic evidence. We're talking real code changes, actual console logs, and genuine on-site developer observations. So this specific kiosk was trying to track 4 highly specific and honestly pretty complex interaction tasks. First up, a 2-hand bowing motion. Second, a single-hand fist-shaking gesture. Third, a 2-hand catching control mechanic. And finally, hovering over nodes in a knowledge graph. Now notice how these aren't just your standard static poses. They're continuous, complex processes. You don't just be in a bow, you transition into it, hold it, and transition out of it. It's a whole flow. By painstakingly digging through those 8 repair logs, the engineering researchers extracted exactly 20 distinct failure instances. That's 20 very specific, documented times where the AI model was running just fine, but the actual user interaction totally and completely collapsed. Which brings us to section 3, 6 ways gestures actually fail. We are going to categorize the exact, let's call it the cause of death, for these 20 failed interactions. The researchers essentially organized these failures into 6 distinct runtime classes. We've got model output degeneration, temporal mismatch, geometric scale instability, coordinate rendering mismatch, runtime lifecycle failure, and feedback synchronization. Now, I really want to stress this point. These are system-level runtime failures. These aren't just, oh, the AI made a bad prediction. No. These happen when the entire architecture surrounding the AI totally fails to translate the model's output into a usable reality. Now, what's really interesting about this slide is how geometric scale instability affects that fist-shaking gesture. Imagine a user standing 2 or maybe 3 meters away from the kiosk. At that distance, their hand occupies this tiny, tiny little region of the camera view. So at that scale, even a minuscule bit of mathematical jitter in the hand landmark gets amplified massively by the system's ratio computations. If your code is using a single point threshold to decide if a hand is a fist or not, that amplified jitter causes the system to violently flip between fist and non-fist states every few milliseconds. To the user, their perfectly solid fist shake just registers as broken, glitchy, random noise on the screen. And this actually brings us to a really profound lesson from the two-hand bowing failure. The quote is, "Parameter tuning does not replace state recovery." See, when the system failed to recognize overlapping hands during a really fast bow, the developers first tried to fix it the way we all do, by tweaking confidence thresholds and expanding tolerance windows. But it didn't work. Why? Because the low-level model was physically degenerating two overlapping hands into one single hand. No amount of parameter tuning is going to fix your system if your architecture lacks a semantic state recovery path to actually handle those degraded inputs. The code was literally freezing up because a variable that was actively looking for two hands just completely stopped updating. And of course, we absolutely can't ignore life cycle and feedback synchronization. Public kiosks, they run for days at a time. If you don't properly release memory when a user walks away, your rendering loop is going to stutter. Or consider this wild feedback synchronization issue. In one of the logs, the AI actually recognized a gesture perfectly, but there was an 800 millisecond debounce delay. A brief pause programmed in just to prevent accidental double inputs. Well, that delay overlapped with the UI's speech playback, so an audio failure branch ended up overwriting the completion prompt. Think about that. The AI worked flawlessly, but because the UI feedback was out of sync, the user perceived the entire interaction as a total failure. Let's turn to section 4, from frames to events. So we are shifting here from diagnosing the illness to actually prescribing the architectural blueprint to cure these failures. And this right here brilliantly illustrates the massive mindset shift that developers really need to make. Think of it like a micro to macro analogy. A recognized frame, that raw output you get from the vision model, is really just a single letter. But a user's actual interaction event, that is the whole sentence. You can't understand a sentence by just confirming that the letter A exists, right? Developers absolutely must build a runtime abstraction layer that sits between the raw AI model and the final user interface task to actually piece those letters together into something meaningful. Let's move to this slide and see how this builds into a real, functional, event-level confirmation procedure. Here is the step-by-step for that abstraction layer. Step 1, frame output evaluation. You've got to reject low-confidence or physically impossible observations right out of the gate. Step 2, scale normalization. You adjust the data based on whether the user is 1 meter away or 3 meters away. Step 3, temporal aggregation and voting. This is crucial. You don't act on just one frame. You aggregate frames over a short time window and require a majority vote to stop that violent boundary flipping we talked about. Step 4, state recovery check. If the hand is briefly lost because it got occluded, you retain the previous semantic state for a short grace period instead of just instantly resetting the whole thing. And finally, step 5, confirmed event dispatch. Only when all these conditions are met and the system isn't stuck in a cooldown state do you actually send that event to the UI. Now, when we map those specific architectural fixes back to our original failure classes, we can really see how this abstraction layer solves the gap. Geometric instability, that gets cured by multi-vector scale normalization and an exponential moving average, or EMA smoothing, basically mathematically averaging out those tiny annoying jitters over time. Rendering mismatch, where the digital skeleton looks totally detached from the user's actual hand, that is fixed by strict coordinate alignment between the AI model space and the UI canvas space. And those feedback sync issues we just mentioned, eliminated using step guards. Step guards lock in sequential movements so they can't be accidentally skipped, paired with precise UI debouncing. This basically proves that event-level engineering, not just throwing better AI models at the problem, is what actually solves the public space gap. Let's wrap things up with section 5, building better public AI. So, what's the ultimate takeaway here for anyone out there deploying these types of systems? Honestly, it all comes down to this core thesis from the source material: user-visible failures are not equivalent to errors in a single model output frame. It's so true. Your system might generate these beautiful, highly accurate, perfect landmarks in 95% of its frames, but if you lack coordinate mapping, If your UI overwrites audio prompts, or if your state machine stubbornly resets the exact moment a hand overlaps, the system fails, the user walks away frustrated. The goal at the end of the day isn't a mathematically perfect frame. The goal is a confirmable, stable event. So I want to leave you with this somewhat provocative question to ponder for your own engineering projects. Is your architecture actually confirming real, continuous user events, or are you just sort of guessing at isolated frames and hoping for the best? Thank you so much for joining me on this explainer today. I really hope this deep dive into the kiosk repair logs has sparked some curiosity and maybe given you a completely new perspective on deploying AI in the real, messy world. Keep building, keep learning, and I'll catch you in the next one.